All right, so the good news, and I feel like many of you might have been stressed by that, but the good news is we're about to emerge from the deep math land and get back into meaningful things. These are some return stuff. Everyone that has something in the stack should be in the room, so hopefully there's no leftovers. But just pass it around. You might or might not have something in that. And if my stapler ran out, so you might have 2 pages that are folded over in the corner. So just make sure you get both of those. At any rate, all right. So I'm going to start. So today we're actually going to get to a pretty nice introduction to the difficulties that general relativity is going to have to face and overcome. And these are going to be stated in terms of things which you're very comfortable with, okay? So let me start just by really hammering home some of the ideas that we've covered recently. So I just want to work through a very quick example. This is something which you should be relatively comfortable with from having done your homework, but I just want to go through a really hardcore example. So recall, oh mighty, that one's already ran out. Please don't be run out. Oh yes, it worked, good, that's awesome. Dx mu prime dx mu prime, okay, which we will often write as d mu x mu prime, d mu prime x mu, okay? This thing is got to be equal to d mu in the sense that this is the inverse of this, okay? So if we wanted to think about this in matrix terms, if this was a matrix M, then this would be its inverse, and this would be the identity. That's the matrix language. This is just the index notation language, okay? So I'm just going to actually run through a very quick, super concrete example of this so that you can kind of appreciate like how these index notation things work and the matrix things work and how these derivatives work and everything. Because from the homework help hours that I assisted in, students were kind of coming to terms with it. And that's fine if you weren't 100% comfortable with it as of the homework quiz, because you will become comfortable with it in the course of this class, because we're going to use this a lot. So here's a really simple example of a coordinate transformation. So we can imagine if we started out with coordinates x1 and x2, that we create the new coordinates x1 prime and x2 prime, by these redefinitions. Okay? So x1 prime, the new x1 prime is just the sum of the old coordinates, and the x2 prime is the difference in the old coordinates. And now we can immediately go ahead and calculate the contributions to this matrix. Okay? So we can do dx1 prime dx1. Any takers? 1. Yeah, it's just 1. It's this easy. How about dx1 prime dx2? It's 1. What about dx2 prime dx1? -1 and dx2 prime dx2? Takers? 1, yeah. Okay? So I want you to keep in mind, and this is the hold on a second. Row, column, row. Yeah, no, these aren't quite right. The derivatives are right, I'm just, my ordering is not quite right. Oh, it actually doesn't matter. It doesn't really matter. Okay, so we can form a matrix from this by identifying, and this is the notation which is perhaps more useful than this, because with this it's hard to figure out what represents the row and what represents the column. because they're right over each other. But here, remember, any index to the left represents the row, and any index to the right represents the column, okay? So we can take dx11 or dx1 prime 1, and we can say that's obviously the first element. And then we can say that the first row, second column is 1, 2, so this is minus 1. And then this is the second row, first column, and then this, of course, is the second row, second column. We can call that a matrix M, okay? Alternatively, we can take this and we can invert it to find what x1 and x2 would be in terms of the new coordinates. So if we did that, we would get 1/2 x1 prime minus 1/2 x2 prime, 1/2 x1 prime plus 1/2 x2 prime, okay? It's literally just solving this set of equations for x1 and x2, which I know you could all do in about 45 seconds, okay? So if we execute the derivatives here, then what we find is dx1 prime is 1/2, dx1 dx2 prime is minus 1/2, dx2 dx1 prime is 1/2, and dx2 dx2 prime is 1/2, okay? Hopefully these derivatives are obvious. Are they not obvious to anyone? Feel free to raise your hand. Okay, so now we can form the matrix of these, and again, this is the 1, 1 term. This is the first row, second column, second row, first column. And sure enough, if you take this matrix and multiply it by that matrix, you'll get the identity. Okay? All right? Any questions about this? I'm just giving you a really concrete example of how to calculate these important coordinate change matrices, because these are the operators which are responsible for coordinate changes. In a manner I'll remind you in just a minute. A better name for them is diffeomorphisms in the fancy manifold lingo. Okay, so moving right along, we are now going to make a brief comparison between special relativity and what we will eventually encounter in general relativity, or what we've already encountered but will be extended. So hopefully, you should all be comfortable now with the fact that in special relativity, we have that a vector transforms, or the components of a vector transform into the components of a new vector with the application of a Lorentz transformation operator. Okay? And incidentally, the components of a dual vector also change with the application of the inverse of that Lorentz transformation operator. In general relativity, hopefully by now you've at least kind of become comfortable with the idea that the transformation is now given by dx mu prime dx mu v mu, and for dual vector components we have dx mu dx mu prime omega mu. Okay? Now, Daniel, what can you tell me about lambdas? They are matrices which are composed of what? Are they composed of functions?
No, those are composed of functions, are they?
Well, I mean, they're not, are they position dependent?
Oh, yes. No?
No.
Oh, they're just scalars?
Well, so you're either rotating by an angle, and you're rotating by that angle everywhere, or you're boosting by a velocity, and you're boosting by the same velocity everywhere. These are what are called global transformations. If you might remember my discussion from, I think, the first or second lecture over different types of groups, or the transformations that we consider, you have global versus local. Global transformations mean if you're going to do a transformation, you're going to do it to every point in space or space-time exactly the same way. You're not going to do it one way here and a different way here, okay? These, on the other hand, are local transformations. What that means is that this transformation matrix can actually have functions in it, which differ based on where you are. They're functions of your space-time position. Okay? But this is how we defined a local transformation. Remember I had a set of dots and I said, okay, let's do a global let's do a global transformation of displacement. Well, there you go, it looks the same. A local one might actually end up something like this. Okay, because you can translate each of these dots differently in a local transformation. They all get transformed in the same way in a global transformation. The transformation is position, it's dot dependent here. Here it's position dependent. Okay? Now, one way to notate this is to say if we're working in the coordinates t, x, y, z, then the transformation matrix might be a function of the original coordinates. That is, it might depend on where you are as to exactly what the transformation looks like. Okay? Now, I'm stressing this because of one incredibly important observation. This thing is made of constants. This thing can have functions in it. These include these, because I could have the freedom to transform everything differently, and then I just decide to transform everything globally. So this is a much larger set than this. This contains these, but it also contains a lot more. Okay? But here's the really big observation. What's the derivative of this? With respect to where you are, with respect to x mu. It's 0. It's just a bunch of constants. What's the derivative of this? Not necessarily 0. Okay? This is going to play a very, very important role for the following reason. Are you ready? Consider the derivative of a tensor. I'll just take a simple dual vector tensor. It doesn't really matter. If we transform this, you might say to yourself, well, this is a two-rank tensor. It's got two lower indices. I know how to transform each of these indices, right? Well, that's one method, but what we should do is we should explore exactly how this transforms. Because as it will turn out, this is not a tensor. Let's find out why. First of all, I know how the derivative transforms, okay? This transforms as dx mu, dx mu prime, d mu, okay? This is the transformation of the derivative. The transformation of the tensor is dx nu, dx nu prime, t nu. Okay? Everybody on board? Now, Matthew, do you see a problem? how would this transform if this were actually a tensor?
It would be invariant, right? So
Well, as a tensor, it would be invariant, but these are the components of a tensor. So how would they transform if this is truly a second-rank tensor?
it all transforms the same.
Yeah, they would transform in the same way. So ideally, this would transform as dx mu, sorry, dx mu, d mu, t nu, prime, prime. This is the tensor transformation rule, remember? You just throw on a transformation matrix for each index, and that's it. But here's the important part, it's the placement. These things are all the way to the left. So now, I would like for Skylar, are you here, Skylar? Skylar, to tell me, can I take this and move it to the left? Can I just push it out of sight of this derivative?
No, I don't know why.
Okay. You're absolutely right. You can't. Because these are functions of where you are. The derivative will act on them. So if I actually write out what I get when I do this, well, this is a product of two things, so I can just use the product rule from calculus. Okay, I can hit this one and then just multiply by this one, and then hit this one and multiply by this one. The second term just gives me back what I wanted. But I also get yeah. Yeah, I'll do it like this. Okay? Again, this is just letting the derivative act on t nu first, and then pulling this guy over here, and then this is actually letting the derivative act on that transformation matrix, which is going to be non-zero in general, okay? This is tensorial, this is not. Unless, what?
The derivative of the rotation matrix is 0.
Or better still, if you're dealing with a transformation which is
Global.
global, right? Because a global transformation, the form of this is just a bunch of constants, i.e. these. This derivative would be 0, and it would transform like a tensor. That is why in special relativity, this is a tensor. In special relativity, the derivative of a tensor is a tensor. Because in special relativity, these matrices are just constants. So this derivative is 0. And the transformation of this is just the tensorial part. However, if you are doing general coordinate transformations where this can be a function of where you are, then this derivative is not 0. So this thing is not a tensor. Okay? But hopefully you might remember that I stressed to you the importance of actually working with tensors. Because tensors transform in an appropriate manner, and so you can form invariants. Okay? Well, this is not a tensor. So how are we going to fix it? We can restrict the transformations to these guys and just say general relativity sucks, we'll just do special relativity. Boom! Or we can do what?
How do I answer this?
No. because I know you know the answer, Ross. We'll have to change something. What do you think it might be?
Do we just restrict ourselves to a particular kind of T?
Nope.
We bend the spatial coordinates so that our right side is 0?
Nope.
Do we do something like in particle physics where we introduce a gauge?
That's exactly right. It's going to be exactly like particle physics. We're going to introduce a new derivative. We're going to introduce a different derivative, which is designed explicitly such that the new derivative of a tensor is a tensor. It's that simple. Okay? Now I'm hinting at it now. We are going to develop that in detail during our next lecture. But I'm going to give you even more evidence for what to expect. Okay? But this idea that the derivative is broken and that you need to fix it is one of the primary observations and techniques in generating the standard model forces in particle physics from the symmetry principle. So I do this because hopefully if you've taken particle, or if you're at least interested in particle, you'll see the connection. Okay. So with that in mind, let us point out some more things that we're going to need. A new derivative is definitely one of them. So now recall that the metric, okay, that's a very special tensor, and it provides the map from an element of a vector space into a corresponding element of the dual vector space. All right? So the metric can take a tensor and lower one of its indices, and these are not totally unrelated tensors. Okay, and I can apply another metric to lower the second index if I like. Okay? This is, of course, in contrast to using just an arbitrary tensor to lower the index, because this will lower the index, but it's going to give me an unrelated thing. Okay, so we might as well call this B nu beta. Okay? So I know it's just notation, but it's really to remind you, this is a different version of this. This is a totally different object than this. Okay, so the metric, you keep the same symbol. If you use any other tensor to lower it, you better give it a new symbol. All right? Now, recall that the metric has this interesting property that it has an inverse, which is just a metric with two upper components. Okay? This is obviously true for Minkowski space, where the metric is -1, 1, 1, 1, and so is the inverse. But this is true in general. Okay? So another way to say this is that G alpha lambda is G lambda nu inverse. And you can contrast this with the fact that T mu is not T mu inverse. Okay? The metric with its upper indices is the inverse of the lower index metric. However, if I take a tensor with upper indices, that is not the inverse of the tensor with lower indices. Okay? Now, hold on. Okay, so one more observation, and then we'll move on to probably using some of this as well. So imagine if I take R3, this is just normal three-dimensional Euclidean space, with spherical polar coordinates. Okay? Some of you might wonder, what does the metric look like? Well, first of all, this is flat space, so you might think that it looks like the identity. But the identity is only relevant if you're working with rectangular coordinates, x, y, and z. Okay? These are spherical polar coordinates, so the metric takes a different form. It actually takes the form 1 r squared sine squared theta. Okay, and let's see how we use this. So if I want the line element squared ds squared, what I do is I take dx mu, g mu nu, dx nu, okay, where a dx vector is just dr, d theta, d phi, all right? And so, of course, this just becomes dr, d theta, d phi, 1 r squared sine squared theta, dr, d theta, d phi. And this, of course, is going to give us dr squared plus r squared d theta squared plus r squared sine squared theta dp squared. Okay? Which hopefully is the familiar line element. Now here's an important observation. This line element is one way of conveying what the matrix is, or sorry, what the metric is in its matrix form. If you know what the line element is and you know what coordinates you're working with, you can extract the matrix form of the metric. Really, you just read off the coefficients here. The matrix is 1 r squared sine squared theta. Okay, so we can either work with the line, man, my memory is just going today. We can either work with the interval squared, or we can work with the matrix form of the metric. Either one of those is a good illustration of what the metric is. Yeah?
Is the metric always going to be a diagonal matrix then?
In this class, it will mostly be a diagonal, but it's certainly not restricted to being a diagonal. Yeah. You can make the metric non-diagonal pretty simply, actually. Okay, but almost every metric that we'll work with will be diagonal in this class. Now here's an important observation. The metric is this. It is not this. Remember, in special relativity, eta mu nu has the same components as eta mu nu, because the inverse of minus 1, 1, 1, 1 was minus 1, 1, 1, 1. Here, that's not the case. In this case, it would be 1 over r squared, 1 over r squared sine squared theta, which is definitely different than the metric. Okay? All right. Now, I'm going to erase this, even though I'm going to end up writing it back on the board in a few minutes. Okay, so first of all, a single space can emit many different metrics. It's not that a space has one metric. You can have many different metrics. Okay? In fact, what coordinates you use for the space is going to influence the metric. So for example, in R3 with x, y, and z, the metric is, of course, the identity. Okay? In R3 with r theta phi, the metric takes this form. Okay? Now, I just want you to notice these are describing the same space. Here the metric is trivial. Here the metric is not trivial. This metric is position dependent. If you change what r value you're talking about, the metric changes. If you change what theta angle you're talking about, the metric changes. Okay? So in general, we should expect the metric to be a function of where you are, not this good old identity constant thing that we've been experiencing from special relativity. What's interesting is we could have used this metric in special relativity, because special relativity is just a theory of flat space. So we could have used this and it would have screwed things up, okay, but it would have been valid. Now, here's an interesting question. How can we figure out if a space is curved or not? Well, if you ever see the metric written as a diagonal of constants, then I guarantee you this is a flat space. And I know right now I'm using the word flat and curved, and you kind of have a sense of what that means, but we're going to give it a very, very solid definition in due time. You might look at this, and if I used my head to cover up what space it is the metric for, you might think, oh, this is curved. No, this is flat space. This is flat three-dimensional space. Okay? So it's kind of hard to look at the metric to figure out whether a space is flat or curved. In fact, let me give you this example. Flat or curved? Flat or curved? Oh, let me pick a victim. Hannah. Flat or curved?
Given context clues and what I think that first coordinate might represent, I would say curve.
You think it's curved? Say it again.
I think so, but I don't know.
You think it's curved? Well, let me show you what space this describes. This is the metric for S2. Is S2 curved? Hell yes, it is. It's a ball. It's got curvature. Okay? If you think about it, if you work in terms of theta and phi, the position where you are, this is the metric that you have to use, where r is just the radius of the sphere. That's why r is no longer low. Okay? The point I'm trying to make is, if you just look at the metric, it's hard to figure out whether the space is curved or flat. Okay, so we need a better tool, and of course we're going to develop a very rigorous tool. Okay? It turns out that one of the things to remember from our discussion about what spaces are important in general relativity is that they are manifolds. And one of the key characteristics of manifolds is that if you go to a very small neighborhood of any point in the space, you can make it such that things look like they're in flat space. You can only do that in a small region if the space is curved. Okay? But nonetheless, you can always take any point in the space and write things, and it's basically your choice of coordinates, such that that part of space looks like it's flat, even if the space is curved. Only that region looks flat. Now we're going to figure out what we mean by flatness, but basically what it means is that in the neighborhood of that point, the metric will take the form of either a Euclidean signature metric, that's if everything's spatial, or a Lorentzian signature metric. And I mean, if we're going to do 4 dimensions, I'll just put in 4 terms. Okay? So if I'm in 4-dimensional space, not space-time, but space, if it's a manifold, I can make the metric around in a small neighborhood of a point look like this. If it's in space-time, I can make the metric around a little point look like this. But I can do one step better, because I can also make it such that the derivative of the metric is approximately 0. Or it is 0 near this point in question. Okay? Now, I I say that you can do this with a certain set of coordinates, and these coordinates have a special name. They're called local inertial coordinates. Okay, the word inertial is just implying that everything is flat. Everything is acting like there's nothing around. There's no curvature, there's no gravity or anything. So let me give you an example of a local inertial coordinate system in order to drive this point home. And also, to give you a good sense for what we will need in order to define the curvature of a space. So consider the two-sphere. Embedded in 3 dimensions. All right, and of course we have these normal angular coordinates. We have phi here. And the angle theta here. Oops, nope. Theta comes from the North Pole. Okay, so you should all be somewhat familiar with polar coordinates, spherical polar coordinates. And of course, there's no r coordinate here because we're only looking at the surface of this sphere, so it's got a fixed value of r. So we don't need to worry about r as a coordinate. Okay, so first of all, we can always relate the x position as r sine theta cosine phi. The y position is r sine theta sine phi. And of course the z position is just r cosine theta. Okay? So these are the x, y, z coordinates for points on the surface of this sphere. And then we know that the metric on the sphere, which I can write as a line interval, is r squared d theta squared plus r squared sine squared theta d phi squared, which of course just tells us that this is the metric I wrote earlier. Okay? Now, everything I've told you right now is just for this entire space, but what we're going to do is we now want to pick a point on the sphere, and we want to build local inertial coordinates around that point. What special point on the sphere may we consider? We can consider any point on the sphere, but what's the obvious candidate?
0, 0. Not x, y, but in terms of theta.
Ho, ho, ho! Merry Christmas. We'll do the North Pole. Okay? We'll do the North Pole. I know you're trying to be fun. Okay, here we go. So we're going to do the North Pole. And if we go to the North Pole, that's basically taking theta to 0, which makes the metric kind of a mess. This is a highly degenerate form for a 2x2 matrix. So working in terms of theta and phi are obviously not good coordinates. We need a different set of coordinates in order to describe what's going on around the z, this North Pole. Okay? So we'll do the following. Let's choose x equals r theta cosine phi, and y equals r theta sine phi, which is just the small angle approximation lent to this theta in sine theta, where the first term is theta. And then the z coordinate, we're just going to take the z coordinate to be fixed. So we're not going to use it. So if you're at the North Pole and you move a small distance away from the North Pole, your z coordinate won't really change. Your x and your y components will, and they'll change according to these formulas. Where again, we're using the small angle approximation on the theta. The phi, we're not using a small angle because you can go all the way around the North Pole, it's staying very close to it. Theta is measuring your distance from the North Pole, and if you're going to stay near the North Pole, theta has to be small. Okay? So here we go. Let's invert these. So theta equals the square root of x squared plus y squared over r. D theta is 1 over r times the square root of x squared plus y squared times x dx plus y dy. Okay? Does everybody understand how I would do this? If I wanted to figure out theta, I would square this and I would add it to this squared, because then cosine squared plus sine squared is 1. And now I've got x squared plus y squared, r squared, theta squared, r squared. Well, that gives me this. And then I just do d theta of that, where I have to do dx, dy in this thing. Okay? All right? We can similarly figure out phi. Phi will be the inverse tangent of y over x. Hopefully this is obvious, especially after your homework. If you take y over x, the r thetas cancel, and you're left with sine phi over cosine phi, which is just tangent phi, so phi itself is the inverse tangent. And then if you do d phi, which hopefully if you got through all of the homework, you realize taking the derivative of an inverse tangent is sometimes required. It ends up giving you that. Okay? All right. So now what we can do is we can take the metric in the xy coordinates, or sorry, in the theta phi coordinates, and we can now figure out what form this takes in the xy coordinates. Okay? By everywhere we see a theta, replacing it with this expression, and then everywhere we see d theta, replacing it with this expression, and then replacing d phi. Okay? So obviously this can get nasty, and it will a little bit, but here we go. So we're going to have x squared over x squared plus y squared plus r squared sine squared times, or the argument of the sine function is square root of x squared plus y squared over r, and this is times y squared over x squared plus y squared squared times dx squared, and it's going to get worse. Y squared over x squared plus y squared plus r squared sine squared of root x squared plus y squared over r. I feel like I should just sing this instead of writing it and speaking it. Over x squared plus y squared squared bracket dy squared. Okay, fine. I won't sing it. But you asked me if metrics were always diagonal. This one's not, because I have a term which is on the off diagonal. Okay? That's ugly as hell. That's the metric. Isn't that awesome? No, it's not awesome at all. It sucks. Okay, so let's just take advantage of the fact that we know that x and y are going to be small. Because we're in a local neighborhood at this point. So keeping the x and y values small is what it means to be in a neighborhood of that point. So of course, if it's small, then we can of course take sine of root x squared plus y squared over r and we can expand it into root of x squared plus y squared over r minus 1/6 x squared plus y squared to the 3/2 over r cubed plus additional terms. And if we do that, then our metric ends up in the approximate form 1 minus 2y squared over 3r squared plus dot 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 dx squared plus 1 minus 2x squared over 3r squared plus dot 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 dy squared plus 4xy over 3r squared plus dot 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 dx dy. Okay? That's a little prettier. Or if you want the matrix form of this, we can write it as 1 minus 2y squared over 3r squared, 1 minus 2x squared over 3r squared, and then 2xy over 3r squared, 2xy over 3r squared, where all of these have a plus dot dot dot. So I'm giving you the lowest order terms for each of these. All right? Are you ready? Sam, can you hear me?
Yeah.
Sam, hopefully you can see this because you're looking through that camera, but you also have the notes. What is the form of our metric at x equals y equals 0? That is at the North Pole.
1001.
Exactly. As promised, at the point of interest, the metric is the metric of flat space. Remember, that is not what happened if we tried to use the theta phi coordinates. Because taking theta to 0 gave us r squared 0, 0, 0, which did not work. But here you go. Better still, guess. Guess? Okay, guess.
Yes.
What is the derivative of that metric at the points x equals y equals 0?
Is it 0?
It's 0. I mean, look at it. The derivative of 1 is obviously 0. These are all quadratic. So if you take the derivative once, you're going to have a y left here, an x or a y, depending what you take the derivative of here, and an x here. And then you set x, y equals to 0, so the whole thing becomes 0. As promised, in the local inertial coordinate system, the metric is locally flat, and the derivative of it is 0. All right? Well, that's local. I mean, yeah. Woo, 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 yeah, yes. Here's the most important observation. What will not be 0? What will not be 0 even if I plug in x equals y equals 0? The second derivative. Notice, if I take the second derivative, I'm just going to end up with a constant here, a constant here, a constant here, a constant here. Plugging in the values doesn't change it. So perhaps, and this in fact turns out to be true, considering the second derivative is where we're going to get an honest measure of curvature. So we can expect that whatever quantity we use to define the curvature of a manifold it is going to depend on the second derivative of the metric. Because this thing is curved everywhere. There's no spot on it that's not curved. We can choose coordinates to make this look somewhat flat in the sense that the metric takes a form and the derivative of the metric is 0, but the second derivative will still not vanish. The second derivative will be non-zero over this whole damn thing. Okay? So we are going to build something out of the second derivative of the metric in order to do this. Okay, and that's going to come in time. However, there is an extra feature to this local inertial coordinate story, and that is the following. If a space is curved, you can pick any point in the space, and in the neighborhood of that point, you can make space-time look flat. Okay? So here's what we can do. If there's a process happening at this point, say the collision of two things, we can choose to work with coordinates such that that collision looks like it's taking place in flat space. That'll be easier to analyze. And here's the incredibly important observation. As long as the physics we use to describe what is going on is written in terms of tensors, true, honest-to-God tensors, whatever we write will be true in general. It'll be true even if you transform away from flat space to curved space. This is a method for doing calculations in general relativity. If you want to know what's going on right here, go to the local inertial coordinates. So you're using flat space, which is super easy. Make sure you write everything in terms of tensors, and then what you've written is true everywhere. It's pretty magnificent, right? That's going to let us dodge trying to write down equations directly in curved space. Okay? But of course, being able to do this is going to require something like that to be a tensor. So this is one more reason why this thing not being a tensor as it is breaking the theory, and we have to fix it. And the way we're going to fix it is by reintroducing the derivative. And we'll talk about that next time.